Hi ladies and gentlemen, we are into section 2.3. Today will be a reasonably short day, and so let's just jump right into it. What we're going to do is we're going to talk about the LU decomposition, which is largely based upon the conversation that we had previously from Gaussian elimination. So we see here a little bit about what elimination costs. This is not really a topic for Math 344, but there are just a couple of things that are important for you to keep in mind when it comes to computational expense. And that's really what these two conversations here are about. And then, right, we have a couple of proofs of A equals LU. Of course, we don't do proofs in this class, but there is information for us to learn from the proofs. So starting out here, it's really a conversation about the inverse and the application of solving systems of equations to multiple right-hand side vectors. We'll get to that in a second. The first thing I want to do is talk a little bit about Gauss-Jordan elimination. And what I'm going to do is I'm going to review for us here. We have the conversation. Here's a system of equations. We know we can convert that into matrix vector form. From the matrix vector form, we do an augmented matrix, and then we apply Gaussian elimination, and this is what we've been talking about. This is the result of the Gaussian elimination here. What I want to do is demonstrate for you Jordan elimination, which is taking this all the way to where we have leading ones in our pivot locations, and we have eliminated going back up. So we talked about this briefly, but Gauss-Jordan elimination is using the pivots now to eliminate going back up. Gaussian elimination, we eliminate down. The Gauss-Jordan, the Jordan part of it, we eliminate on the way back up. So let me just show you quickly in MATLAB what that looks like. So here's the matrix that we have over here. I've called it C. And let me just demonstrate for you. We're going to go C, and we're going to take the third row. We're still doing row operations, just like we do for Gaussian elimination. And we're going to take this, and we are going to take the third row, and we're going to divide. Sorry, I'm having typing problems here. We're going to divide by the entry that is at the pivot. And we can see what that's going to do. That created a 1 down here, and that's what we're after. We're going to turn the pivots into leading ones, and then we're going to eliminate on the way back up. So now we're going to replace the second row with the second row minus whatever entry, and this is important for generalizing this idea, whatever entry is at 2, 3. So we're going to take whatever this entry is, which happens to be 1, multiplied times the third row. So the multiplier here, which is really the elimination number that we're using, is the negative of whatever that value happens to be, because we have created a 1 down here in the pivot. So when we hit that, we can see that's exactly what we have. As we discussed when we were talking Gaussian elimination, just a simple up arrow. And now what we're going to do is we're going to replace the first row with the current first row, and then we're going to subtract off this multiplier times the third row. So we're using the third row to eliminate up here. And the reason we're working from the bottom going back up is because the 2 zeros here are not going to impact any of the Gaussian elimination that we've already conducted. And so we can see we've used this 1 to eliminate on the way back up. And we automatically see the benefits of this. We see that x3 is equal to 2. And now we're going to divide through by the 1. Of course, we don't need to do that because it's already a 1, but we would turn it into a leading 1 if it was some other number. And we can see that x2 is equal to 2 as well. So the last thing we're going to do is we're going to come up and we're going to use this value to eliminate. So we have C1 comma colon is going to be equal to first row minus whatever this value here is. So that's C, and that is first row, second column, times, and now we're eliminating with the second row. So this is C2 comma colon. And we can see the elimination has happened here. The very last step is to make a leading 1 in the first row. So the first row is going to be equal to the first row divided by whatever the value is that's in that pivot currently. And now what we have is the result of Gauss-Jordan elimination. And the one of the benefits of this is the fact that we could just read the solutions off. x1 is -1, x2 is 2, and x3 is 2, as we saw previously. So that's Gauss-Jordan elimination. That's the process. Let's talk a little bit about this conversation here. I think it's a little bit confusing, so let me explain exactly what's going on. What he is saying, and this is really an important idea, is, hey, look, doing Gaussian elimination or Gauss-Jordan elimination is expensive. Computationally, it's expensive. So what we'd like to be able to do is solve for multiple b vectors, right-hand side vectors, simultaneously. And we can do that. So what he's done here in general is he's taken the equations a x vector sub I is equal to I e hat rather sub I, and he has listed them all simultaneously. And what we can see is that if we perform Gaussian elimination, then we are going to be solving for all of the x vectors associated with the right-hand side vectors. Let me write that out. So he's taken and he's set up AXI equals E hat I, and he has built an augmented matrix, which is really A augmented with E1 hat and E2 hat and E3 hat and however many we want. In this case, he's done 1, 2, and 3. And now when we do Gauss-Jordan elimination on this, we are going to end up with the solutions for all 3 of these right-hand side vectors. And that's the conversation he's having about here for finding the inverse. The reason that he's picked the standard basis vectors is because now he has set this up. This is exactly the same as this. And when we do Gauss-Jordan elimination, what we're going to end up with, if A is invertible, we're going to end up with the identity matrix, as we saw in MATLAB. And what's going to be left over here is the inverse of A. So this is a way in which we can find the inverse for a matrix using a reasonably fast algorithm. I mean, it's not very fast. It's order n cubed, but that's also not a terrible way to calculate the inverse. And so he really highlights for us with this comment right here. The key point is that the elimination steps of A only have to be done once, because when we are operating on the augmented matrix with several right-hand side vectors, we are operating on all of those simultaneously. All right, the conversation about the cost of elimination. This is one of the niet topics. If you look in the syllabus, we are not discussing the cost other than 2 facts that you have to realize. One of them is the expense of actually doing Gaussian or Gauss-Jordan elimination is order n cubed. So when the problem is size n by n for a square system, it costs us about n cubed operations. The back substitution, and this is the point he's making in the introductory part of section 2.3, the back substitution only costs us n squared computations. So once we've done the process of Gaussian elimination on the A matrix with all of these right-hand side vectors, we can solve for the x solutions for each of the right-hand side vectors respectively, and it only costs us n squared computations to do that, which is obviously much, much lower for large matrices than the n cubed it took us to work this out in the first place. So that's really the only part of the conversation that you have to follow along with there. All right, so proving, we're not going to prove anything, but we are going to learn from the proofs. We talked about this previously when we were looking at the elimination matrices and how they're doing Gauss-Jordan elimination for us. But the 2 key items here are the fortuitous facts. So the first fortuitous fact is the notion that we're going to take the inverse of each of these matrices, these elimination matrices, and we're going to be able to find it without doing any calculation. We know automatically what the inverse is going to be for each elimination step that we are conducting. That's the first thing. So let me just write this out. The E21 inverse matrix is easy. And that's true for every one of these, right? So it's not special to E21. Every one of our elimination matrices, it's easy for us to find this inverse. We don't have to do any computation at all. The second fortuitous fact is this one here, which is the fact that when we're doing the multiplication of these inverses that we've calculated, so recall the way this whole thing is set up, we have, for example, E32 and then E31 and E21. We've applied all of those to A to get an upper triangular matrix. Then what we did is we said, well, A is equal to, and we did the inverses, E32 inverse U, E31 inverse, and then E21 inverse. And we've already said finding the inverses is easy. So the other part that is easy, fortuitous fact number 2, is taking the product of these matrices, which normally matrix-matrix multiplication is order n cubed. We don't have any calculations to do. We know exactly where the values are going to fall for these elimination matrices. And that's what I've highlighted over here. The L values are all automatically dropped straight into this matrix. So you remember that this is the E inverse times U, which is the same as LU, because the inverse of all of these elimination matrices put together is the lower triangular matrix we're after. So review those two facts. We talked about those already. I'm not going to spend much time on that. So now what we're going to do is take a look at this important idea. You remember we talked about A is equal to C times R, where C contains a set of linearly independent columns from A, and R contains the information for us to be able to reconstruct the matrix A using the linearly independent columns. And that's regardless of the rank of A. We can set this up and make this work. So what he's saying in this little box right here is a similar type of thing, except now thinking about this as the rows from the LU decomposition. And what he's saying is, hey, if we grab one of these rows and then do like we've talked about and sweep it through the U matrix, right? So let's be clear, this is LU, and that's equal to the A matrix that we have over here, so this is equal to A. He's saying if we grab that L and we sweep it through the rows of U, we can understand how the rows of the A matrix are reconstructed from LU. So it's very easy. For the first one, we see, hey, the first one is just the same first row of U. So the first row of U is the first row of A. And then moving on, the second row of A is equal to 2 times the first row of U plus 1 times the second row of U. That information is contained in the L matrix. So that's what he's talking about over here, is the information that we have gathered from the LU decomposition. I would point out, he doesn't really make this point, but it's worth noting, the same can be said if we think about the columns of U. If we grab that column of U and sweep through the columns that are in L, we can understand how each column of A is reconstructed from LU. It provides us the same type of information as this does. It provides us a way from the decomposition to understand how A is reconstructed from the product of these two matrices. So that's an important idea, and it's worth looking through, making sure you understand that. One other item that he hits on right here, this is all under his second proof of LU, which again, we're not so interested in the proof, but we are interested in these ideas. What he talks about here is the information from a matrix product as a sum of rank 1 matrices. So he tells us the following. Look, this is really equal to the first column of L and the first row of U, this outer product that we talked about. So we take the outer product 1, 2, negative 1, along with 2, 4, negative 2, and I'll just write over here on the side what that's equal to. So that's 1 to negative 1. Sorry, it's multiplied times 2. So that's actually 2, 4, negative 2, and then multiplied by 4. 4, 8, negative 4, and then multiplied by negative 2. Negative 2, negative 4, 2. And this is the product that we have from this first outer product that we construct. And what you'll notice is, pay particular attention, this part of the rank 1 matrix matches exactly with what we have here. Then what we do is we add in the next rank 1 matrix. The next rank 1 matrix is the product of the second column of L and the second row of U. So we're taking and we're adding 0, 1, 1 along with 0, 1, 1. And that, again, let me just point out what that is. This is going to be 0, 1, 1. Whoop, it's 0, 0, 0 because it's multiplied by 0. Then it's 0, 1, 1. And then it's 0, 1, 1. Notice that we have no information in the top left portion. Because of the way the LU is constructed, we are not going to contribute any non-zero information. That's already set up as we saw here. So the next piece of information that we have, when we think about it this way, is, and let me change to the cyan, we have this piece of information. Okay? And so we can see that we're going to take that along with this piece here, and we're going to add those together to come up with the A piece that's right here. So we take those two pieces, because remember, it's summed. We're adding the rank 1 matrices, and summing those two pieces gives us what we expect. And then finally, what we have is we have the third column of L and the third row here. So we have our third outer product, 0, 0, 1 and 0, 0, 4. And this is just going to be all zeros except for the 4 down here. And then we're taking this 4 and we're adding 1 and we're adding 2. And the result of all of that gives us the 7. So that's the conversation he's having here, is kind of the way in which the LU decomposition breaks down into this sum of rank 1 matrices. We know we can do this with any product when we're talking about a matrix product, but when it comes to the LU decomposition, because of the lower and upper triangular nature of these matrices, we are taking information and basically putting it in concrete at each step along the way. And we are reconstructing the A matrix kind of top left, moving down to the bottom right as we move along. All right, so the last conversation here is elimination without row swaps. So we haven't talked anything about the whole idea of doing row swaps, and that's what we're going to talk about in section 2.4. Let's take a quick look at our homework, the participation questions. So the participation questions here, the first one is about you doing the LU decomposition. So as I demonstrated both today and when we were talking about Gauss elimination, put this matrix into MATLAB and go step by step in order to do the Gaussian elimination, in order to find the L and the U matrices, and use the two fortuitous facts when we're doing the elimination steps that allow us to easily reconstruct the L matrix. I mean, that's what makes this work, are these two fortuitous facts we have right here. All right, so here you're going to do the same thing. Put it into MATLAB and walk through the steps. It's just a 2x2. Augment it with the 2x2 identity matrix and walk through a few steps of Gauss-Jordan elimination in order to create the inverse. And then finally, we're going to take the matrix up here and we're going to demonstrate the sum of the rank 1 matrices from the LU product, which is what I just showed you in this conversation down here. All right, great. We'll see you in class. Thanks.